Hi, everybody. Welcome. Everybody's got their seatbelt on. We got a lot to cover tonight, and we'll try and get right to it. Hopefully, this is all making sense. I know there's been some study groups going on. If you got questions, put them in Discord. I'm trying to keep up with that, and also by all means, email me or you know anything like that. And Paulina too, if you've got issues, she can help you. All right, so we're just skip over this. Class 4, AI for threat detection. Uh, got two assignments due tonight, Jupyter Notebook setup and the data pre-processing. Uh, I am very liberal again about assignments. As long as you get them in, you'll get credit for them. There's no knock if you don't get them in. We all got lives. We all got stuff to do. So it's cool with me. And if you got issues, hit me up. I think a couple people have already. So happy to help. Okay. So the agenda for tonight is we're going to talk about anomaly detection, IDS systems, malware detection, and talk about a case study examining a real-world AI-driven threat detection system. I've put together some cool examples. The notebook is available on GitHub if you want to download it and run it for yourself. And we'll try and run through this. And this hopefully is going to start bringing some of these concepts together. Some feedback that I've gotten is that, hey, when do we get to the cybersecurity stuff? Well, it's here. So we'll talk through this and we'll go forward. And we're going to use synthetic data tonight, but we're going to move to next lesson. We're going to actually use log samples from OSRF, and we'll be able to see some kind of real world examples of what we're talking about. Okay, so hopefully by the end of this class, we'll be able to understand how AI will enhance threat detection, uh, differentiate between anomaly detection, intrusion detection, and malware detection, and be able to evaluate a real-world AI-driven threat detection system. Okay, so we're going to talk about anomaly detection first, and then IDS, AI, and then the case study, and then we can do Q&A. I'm sure people have questions. Hopefully, we're not going to go 90 minutes of instruction. Okay, so before we dive into solutions, let's talk about the problem, right? What are the biggest challenges today in modern threat detection? I know from having been a tier 3 responder and running a blue team, volume is huge, right? Anybody who's in InfoSec today that has anything to do with alerts, you're getting crushed by the volume of alerts, right? And it's like, what garbage? How many false positives? It's the same thing with uh, vulnerability management, software scanning, and testing. So, how do you solve that? These are some of the techniques we're going to be talking about. So, if you're a mid-sized company anymore, I mean, you can process uh, tens of millions, hundreds of millions of maybe even a billion security events. It's crazy. When I ran the blue team at Microsoft, when we would get alerts, we would get, high quality alerts, but we'd still get, 60, 70 a day. It's like, how do you deal with that kind of stuff? Um, velocity is an issue. Advanced persistent threats can establish a toehold pretty fast, right? I've seen it in a couple of minutes. And then you have the variety of attacks, right? Ransomware, supply chain attacks, insider threats. Um, have seen in person all of these things. Supply chain is pretty insidious, but you got to have shields up for that kind of stuff, especially if you're using open source, because you just don't know. So, if you got camera on, quick show of hands, but I mean, everybody who has ever experienced alert fatigue, if you're an InfoSec role, right, raise your hand. I'm raising mine, right? We've all been there. It's like, what the heck am I doing? How do I lots of hands, right on. Yeah, so we, totally been there, and that's where we need to transform with artificial intelligence, right? We need to use machine learning techniques and artificial intelligence to help get us higher quality alerts and get us to quit wasting our time tagging alerts as positive, negative, right? Doing our uh after action report or a post-mortem on a false positive. I mean, how much time does that take, right? So we can use techniques that we're going to learn through the rest of this course to hopefully help resolve some of those things, right? Um, but things are shifting. SOC architecture shifting, security architecture shifting, because we know manual analysis fails and traditional methods are going to struggle. And it's essential that we adopt AI principles, machine learning to train AI so that we can survive, right? If we don't, we're all gonna crumble under. So let's talk about anomaly detection, the core concept, right? Um, Anomaly detection is like your immune system. Your body knows it's healthy and it flags anything unusual, right? You get a cough, you get a fever, your body's telling you there's something off, right? And what we're doing is we're looking for data points that fall outside the normal distribution patterns, right? Think about the bell curve, 3 standard deviations from the mean. Anything outside of that is anomalous, right? So it's in the tails. I think it's about 20%, 10% in each tail is going to be anomalous activity. At least it should be if it's statistically valid. But regardless, right, if you calculate the mean and you look 3 standard deviations from it, anything outside of that, we're going to be interested in and figuring out what's going on. Um, so, an example would be, I think I've used this before. A user typically logs in, let's say from Seattle, and then 3 o'clock in the morning, there's a login by the same person from Romania. Is that normal? It's valid, but how would you ever detect that unless you were looking for anomalous login activity? Companies that do this are like Actimize in your bank, right? A lot of times you can just use your biometrics, but sometimes you get challenged for a login if your bank detects some anomalous patterns, right? They just want to verify that it's actually you and it's not somebody else. Um, we can talk about data transfer. So people always follow patterns. They follow patterns for search. They follow patterns for code completion, those kinds of things. Uh, Database access, those sorts of activities. Let's say a database admin usually accesses 10 to 50 records a day, and they access 50,000. That's something you would want to know about. Um, you know, application behavior, right? Let's say that application uses 50 megs of RAM and now it's using 500 and making network connections, right? We would probably want to know about that. So these are all things that we can do with anomaly detection. So there's 2 kinds of anomaly detection. There's supervised and unsupervised. Most anomaly detection is unsupervised because we don't have labeled attack data. Do you remember when we talked about labeled data? Right? Is if I have a set of data and I've gone through, let's say, like spam, and people have clicked and said this is spam, they're labeling that particular message. And that's how we determine what we use to say what is a positive or negative spam message, and that it will extend to network traffic and a bunch of other stuff, application behavior. But what unsupervised is we don't have a label and we just need to go and look at it and see what is going on and hopefully make some sense out of it. And we'll talk about some of these techniques as we go. Um, and we talk about thresholds, right? What's in and what's out. You've heard me talk about this before, right? Is if let's say your adversary figures out where the threshold is in your algorithm, right, to fire detection or not, or take some kind of action. If they know kind of where that boundary is and they can uh, craft their attack so that it falls within the boundary, they might be able to get through. So we'll talk about more about this in a future session about adversarial AI. But just suffice it to say that there's a balance between false positives and false negatives, and the amount of variation that you allow on that decision boundary is what determines whether you say this is anomalous activity and I should flag it or not, whether it's normal activity and I allow it. So you got to be careful about, sensitivity and specificity, right? Do you want to be right all the time, or do you want to not miss um, a possible attack, right? So that's the precision and recall that we talk about. All right, so think about it for a second, right? There's probably lots of things that you can talk about or think about where anomaly detection would be valuable, probably in the work you're doing today. Okay, so let's dive in. All right, so what I did is I went through and I used AI to write some code to go through and create all these great visualizations. This is essentially synthetic data that I've created, and then I've populated some graphs and visuals so that we can demonstrate the principles that we're talking about today. So this is not actual network traffic. We'll talk about an actual network traffic in a lesson real soon, but this is synthetic traffic that's been generated just to illustrate the principles that we have here. Okay, so what this is this is analysis of normal versus anomalous network behavior. So this is the difference between normal and not normal, right? Where's Waldo, right? Waldo lives in the big blue pile there, and not Waldo lives in those red bars going out. You can see this is an area graph, right? We're looking at frequency. This is pretty simple. These are, we're looking at packet size, duration, source bytes, and destination bytes. And this gives us kind of a clear picture based on the network traffic sample that we generated, what's normal and what's anomalous, right? And we're going to use algorithms to help figure this out as we go further into this lesson. So here's some key points, right? Normal traffic is consistent patterns. Anomalous traffic has different distributions, right? The citizens of our network generally behave the same, and if you're not a citizen, you're doing something different, right? And what an anomaly detection algorithm will do is it will figure this out, right? It will figure out the distributions, and it will determine what is normal and what is not normal. Okay, so here's the key points. Distribution analysis is we're going to compare the statistical distribution between classes. What do these blue mountains remind you of? A bell curve, maybe, right? And you could probably draw a line down the middle of this bell curve and say, this is the mean, and I have 3 standard deviations, and these red areas would probably fall outside of that, right? We'll take a look at this as we go forward. Visual recognition, you can look at this data if you plot this, and you can see based on this exactly what's going on. You can do feature discrimination, right? What features give us the best signal? We'll talk about this in a little bit, right? There's feature importance, right? The things that weigh most heavily in the decision are the things where we have the most variation around the mean typically, right? And we have tools and techniques that will help us identify this. And then the other thing is a data quality assessment. We don't really have to worry about that because this is synthetic data, but we do want to make sure that it sort of looks like what we would expect from normal network traffic data. If you've ever looked at network traffic data, I started out in this business as a network engineer. That looks pretty normal to me. Okay. So so coming out of this, right, hopefully intuitively you understand what we're talking about when we talk about an anomaly and how that differs from what we would consider to be norm. Okay. So what types of anomalies are there, right? There's three buckets, according to some. I'm sure you could probably find somebody that has more buckets or less buckets. And the way I think about it is this. You have a point anomaly. And a point anomaly is something that sticks out, right? An example might be, let's say we have an analyst who doesn't work on weekends or is on vacation and suddenly they log in at a weird time, like 2 a.m. on a Saturday or Sunday, and they download the customer database, right? So that's a point anomaly. It's not something that goes on continuously. A contextual anomaly. This is what matters most here is sort of the scene that this takes place in, right? So if I was looking at data from physical security and I saw that a night shift guard who I was okay accessing the building at 2 a.m. suddenly was in the CEO's office, I would want to know about something like that. So it's okay for them to be in the building at 2 a.m. because we would expect that, but not necessarily the office. So the context really matters. And this is where AI excels over rule-based systems because we can't think of all the combinations and permutations as humans, and atomic detection relies on that way too much. And that's where you get a lot of noise in your threat streams and things like that. So we'll talk about that further as we go in. So the big challenge is, right, how do we teach a machine about context? And the way that we do it is twofold, right? One is through feature engineering, right? If we're adding features, so if we go through and add columns, if we're doing like binary classification and things like that, that would be adding features, summary, adding a label like malware, not malware. That's all feature engineering. And then we can talk about collective anomalies. So each, let's talk about credit card transactions. So each one looks normal. It's like $50, $75, $60. But if there's 1,000 of them in a sequence from different locations, right, all of a sudden that should be flagged as fraud. If you've ever traveled internationally, usually the first time you try to use your credit card, you're going to get a text from your credit card company saying, "Hey, is this you?" Right? That's an example probably of some of that detection logic. Like APT, for example, right? So individually, a network connection looks benign, but if you look at the pattern, it reveals command and control communication. I've seen this in real life, right? Where you look at NetFlow data and you realize that you have a suspicious endpoint that's beaconing to a known APT address, and you have to flag that down. I can talk about this because it's been published, but we had an issue where we had an APT that gained access through a printer at Microsoft, and they established their toehold and a unpatched IP phone. And the way that we found them was through command and control beacon. So it really happens. Um, and with respect to how you find these kind of things, you need to recognize patterns and look at sequence of activities. And a lot of times, this is where time series really comes into play, right? If you look at time series and see what's going on. And you can use neural network techniques as well. And I would say, think about it this way, right? Which type do you think is probably the hardest to detect? And why would that be, right? So some of these, I won't say any of them are simple, but in my opinion, I don't know, contextual and collective. I would say collective is probably harder, but that's just my opinion. Okay. All right. So let's talk about this a little bit in the context of um, our synthetic data in the notebook that we put together, right? So what this shows is it shows you some unsupervised anomaly detection. And we're using isolation forest, right, which is an unsupervised technique. And this will help us figure out how we can detect unusual patterns, right? Isolation did pretty good. Accuracy was 98%. Precision was 80%. Recall was 100%, right? So we didn't miss anything. And then our F1 score is 0.889. So now here's an important thing. We've talked about F1 score before. Remember that F1 score is sort of the average of precision and recall, and it's preferable to accuracy to tell you how good your algorithm is. If it was perfect, it would be 1. 89% is pretty good, but you can see, it says it's 98% accurate, but the F1 score is lower. And remember that if you're using an algorithm, right, F1 score is probably a better indicator than accuracy of how good your algorithm's doing. And, that will help you decide which direction you want to go with respect to that. So, another thing to remember is isolation forest finds anomalies by randomly selecting features, and it splits the values. So anomalies are easier to isolate, right? Because there's fewer splits needed because the fact of that they're showing so far away from the mean. So it's simpler to tease them out, right? If you look at the graph on the left, it has anomaly score. Anything that is left of 0 into the negative is classified as an anomaly, which shows you where kind of those 20 that are normal that were flagged as an anomaly come from. But we would rather err on the safe side, right? So that's kind of the distribution. And again, there's no labels required because this is unsupervised. Um, we talked about isolation principle, which anomalies are easier to isolate than normal points, right? Because you've got more normal and less anomalies. Um, this is an ensemble method. It uses multiple trees because an isolation forest. We talked about this earlier. This is stuff you probably don't need to remember for now, but think about in the future if you're doing hyperparameter tuning as contamination. That's one I always set at 42. If you run it one time with contamination as one number and then run it again and change contamination, you should get the same results if the algorithm's working properly. So that's a good test. So out of this, you get the performance metrics, accuracy, recall, precision, and recall. We get these histograms and the confusion matrix, which I like, right? This gives you a really good view of how well your algorithm is performing. Okay. All right. So now we're going a little deeper. All right. So this is the same data, but these are some different visualizations. And what we're doing here is we're using another algorithm to figure out where our decision boundary is and to make these cool graphs. Okay. And let me reiterate, I have all this is generated by LLMs. I am not a capable Python programmer who could put something like this together. I'm just a dumb hacker. And this is the kind of results that you're able to get, right? And this is what we're working towards, right? Use your LLM to help get this for you. Maybe I'll start sharing my prompts and you guys can kind of see the journey that I go on to get these graphs. All right. So SVM support vector machine, it creates a non-linear decision boundary, right, around a normal points. It has different kernels. Again, that's a hyperparameter you can tune. Don't worry about that too much right now, but just be aware in the future that if you do use one SVM, you can change the kernel, and you don't need to know about it now, but be aware that there are options. Support vectors define the boundary, right? Fewer points is more efficient. If you look here at this lower left support vectors, right, 98 points, those green triangles, those are all the support vectors, right? So we've got a lot of them because we've kind of got this blob, but you can see that this is still packet size. And down here in the left-hand corner where it's surrounded by the green triangles, which show the decision boundary, that tells you what a normal packet size and duration pair are together, right? And then all these other things that fall outside of that are the anomalies from the test data set. And that's how you would make a decision, right? You can do this same technique using your actual network traffic, and then you'll be able to tease this out. And we'll look at this in a future lesson with respect to the traffic. So the decision function score distribution, this shows you where the decision boundary is for the anomaly, right? It's 0, right? That's the mean, again, mean right in the middle. And everything to the left of it is considered an anomaly. If you zoomed in on it, you would see down there, there's a little bit of blue. That means that those are the things that are actual normal traffic that we flagged as anomalies, which we would prefer to do as opposed to going the other way and not flagging anomalies and saying they're normal traffic. So the key insight here is that normal data gets a positive score and anomalies get a negative score. The decision boundary, again, is 0. Okay, so this next one, this looks pretty cool. This is a 2D decision boundary visualization. This is the actual decision boundary in feature space. You notice it looks a lot like the support vectors, right? That's where that decision boundary, that black line around that blob gets drawn. And that shows you what's in and what's out, right? This is all normal traffic inside of this blob looking thing. And everything outside of it is classified as anomaly, right? This boundary, which you can adjust through hyperparameters, right? You could probably make this bigger and you would be okay, but that depends on how many anomalous pairs that you would want inside of this particular decision boundary. Okay, and then again, remember we talked about scaling, right? The duration is scaled because we have a mean and we have you know, our how many standard deviations we are from the mean. That's what those numbers mean, from 0 to 12 standard deviations, right? Same thing with packet size. 0 is the mean. The two means come together kind of here in the middle of this blob, which means I like it. But this is where you figure out the decision boundary, right? It's the same sort of concept as off here to the left, where we have a decision boundary with a vertical line from the 0. Confusion matrix, we're going to see this a lot. So ask your LLM about confusion matrices. But this is for this particular algorithm. It shows how it performs. You can see that maybe this algorithm doesn't perform that good, right? Because we have things that are labeled normal that are actual anomalies. We could go in and probably play with that and tune some hyperparameters and get that to function better. But this is an indication of how well this SVM algorithm is working, right? We talked about the decision function. Let's talk about the performance comparison. This is a comparison between isolation and forest, which was the previous graph, and with one class SVM. And you can see how they compare, right? And again, F1 score is the gold standard, right? You want the best F1 score. So what this tells me, isolation forest has a F1 score of 0.889. If I look at precision and recall, they're pretty good, 0.1. And then that to me is better because the precision is a lot worse, right? Precision over here, precision versus isolation forest. And then this is parameter sensitivity analysis. We'll talk about this further as we go, we're going to talk about NU, right? This is basically you're telling the algorithm what percentage of it that you expect it to be anomalous. And the way that you tune this is, we'll talk about this again too, is the elbow, right? You see there's this little dip here. That tells us kind of where the best NU parameter value is. So if that was in a different spot, maybe we would want to move it, but this looks pretty good for what we're doing. Again, not critical to remember. Just remember that NU is a hyperparameter that you can tune for one class SVM. All right. So AI enhanced intrusion detection, right? So traditional IDS, I hate IDS, right? What's the difference between a signature based and a rule based? Signature based, we think we're smart and we know everything there is to know, and it matches. It could be Yara rule, whatever. It says this is a bad packet and it flags it or it blocks it or it does something. And it's, lots of false positives, not great performance. There's all kinds of issues. Rule based, it says, certain parameters are in place. It can block, not block, send an alert. So it's a little bit more flexible, right? So limitations of the traditional IDS, I would say it's like having a mugshot, right? Is if you have all the mugshots, all the bad guys, you're fine. You can catch repeat offenders, but if you get new kind of traffic that comes through, it's pretty useless. So it's like if you remember WannaCry 8 years ago, right? It exploited a vulnerability. It didn't have a signature, and then IDS was useless. So suboptimal to say the least. If you're in one of those roles where you're going through and all the time you are dealing with false positives, alerts, and things like that, I feel for you, but hopefully we'll be able to apply some techniques that we learn in this course and help make some sense out of that and add some sanity to the madness. All right, so there's a big change in IDS, right? We have behavioral IDS, which is huge, right? Instead of looking for a known bad pattern, like the mugshot, we learn what good patterns are and we flag deviations, right? So if we looked at that previous traffic example, it was obvious where the anomalies were based on what the normal traffic was. So this is how we focus our time, right? Instead of comparing mugshots, we're looking for bad activity. The machine learning approach is that it uses clustering algorithms like k-means or dbScan, and we'll talk about these further in a bit. And those establish a normal behavior baseline. Less false positives, right? Traditional IDS can have huge false positive rates, right? AI can reduce this down to single digits, hopefully. And this lets your analysts focus on real threats instead of swiveling back and forth in their chair between two different systems, trying to chase ghosts. So a big advantage, right, is that it's adaptive. It gets smarter the more traffic that it sees, much like algorithms that we have, the more data that you throw at them, the better they get, right? So it's important because the algorithms they use update models in real time, and that's super important because it helps make them more effective, right? And I know when I worked with traditional IDS, I wanted to tear my hair out. You're trying to help a customer out, and they're insistent on shooting themselves in the foot, so it can be a real battle. And seems like it's part of the arsenal for better or for worse. So hopefully everybody is working with next generation tooling that works on behavior and has adaptive AI support. Okay, so now let's look at this example. So what we did here is, and you can see this in the notebook, we actually simulate IDS traffic. And what we want to do is we want to say, you know, what does an IDS do? And what we're looking at is this, right? That, we're doing anomaly detection early is what we're trying to do with IDS. And this is unsupervised learning because we don't have labeled data. And what we're doing is we're looking at clusters, right? You can see the clusters here off to the right with these data transfer patterns. Oops, sorry. Do that. And, we can talk about protocol usage, feature correlation, right? What features go together is, if you have high correlation between source bytes and destination bytes, and that's the strongest correlation in this graph, that's probably a good place to look with respect to your IDS. So again, this uses one class SVM, right? It's again unsupervised, and it learns to separate class A from class B, and it learns what's normal and it flags anything that's not. And it's perfect because you have a lot of network traffic, right, and behavior. We don't have examples of all possible attacks. New attacks are coming in constantly, and the unsupervised approach catches these unknown threats. Okay. I'm going to mention NU again, new, right? This is where you tell the algorithm what percentage of expected anomalies. A lot of times you just use 0.1 for 10. I mean, 0.1 or 0.2 is pretty good. 0.1 is balanced. I think it's in the notes. If not, I can share this, right? But you can just say, ask your LLM, how do I choose new for SVM? And it'll tell you. But, 0.1 is conservative, 0.01 is conservative, 0.5 is liberal. Just choose 0.1 if you ever have to choose, right? Your LLM should do it. The other thing with one class is gamma. That is that determines how tight or how loose your boundaries are. There's an option called scale. Just choose scale and run it, and then you can tune that again. That's another hyperparameter. So those are two that you might run across. So the key here is one class SVM learns boundary, right, around normal data, and points outside the boundary are considered anomalies. When do you want to use it? When you have lots of normal data, you need to detect unknown attacks. Normal data is complex nonlinear. And if you have labeled data used a supervised method, SVM probably isn't. So this is really a powerful tool, and you will probably be using this again in your capstone project, and as part of an ensemble method. And it's really good at finding these clusters, right? So if you look at like data transfer patterns, the key here is that you have these different colors that represent the different kinds of attacks, right? So denial of service is up here at the upper right, this big cluster, right? In blue and dark purple. This occurs because of floods. Like, look at the destination bytes and the source bytes are high, right? So you're pumping a lot of traffic through. Probe attacks, right, are blue or teal colored, right? They're if they have low to moderate source bytes and destination bytes. This is port scanning, service enumeration, right? You're not trying to unleash a fire hose against your attacker, but you're still putting a fair amount of traffic in there because you're looking for activity. mapping networks, remote to local attacks, right? Where someone's coming in from the outside, green, yellow here, uh, things like password guessing, buffer overruns, data injection, right? It's a little bit more traffic than a probe attack. And then you have over here, you have the user to root, right? This is privilege elevation kind of thing where you have more traffic associated with it, but it's balanced sort of between source and destination. But this is just an example based on the synthetic data set that we have, right? So what are the key insights here, right? The attack signatures are in the data flow, right? Normal traffic is balanced distribution. If we look here in this first graph, we got all the salmon color, right? Denial of service is it's a lot of traffic, right? Kind of here in the lower corner. And why does it matter for AI, right? So we got to separate features. So each one of these attack detections is based on information from a number of features. You can see that source and destination bytes, right? Those are the features that we use in this particular graph for data transfer patterns. And you can see how those different attacks kind of cluster and stick out. Right? Decision boundaries, AI can draw a decision boundary around these different parameters, right? So it could determine, that anything inside this particular boundary is DOS, or anything that's outside is not DOS, kind of thing. Clustering, you can see that intuitively. Natural groupings that ML algorithms learn, right? And then pattern recognition, right? Each attack occupies a different region of the feature space. So they're distinct, they have different characteristics, and you can see how they're detectable. And these are the techniques that that we use. Okay. So a lot to digest there. Real world is we look at network traffic flow, right? We look at ratios between different kinds of traffic. We flag patterns that don't match normal, right? We know normal looks kind of like the salmon color, and anything that's not normal, we got to figure out how to tease out. And we need to set up alerts, right, for the different areas. And AI systems use these features as inputs to classify, and then you're able to separate them so you get high accuracy. And this lets you detect new attacks that fall into the known pattern regions, right? So pattern regions would be these clusters. All right. And then this is if we were doing a supervised machine learning approach, right? So if we had labeled attack data, we would have a different look, right? A confusion matrix is really clean because we got everything labeled. We know about it. We use random forest to combine the methods and do the decision trees. And remember, again, we've scaled our features, right? So they're standardized, so we aren't getting blown out of proportion by quantity of traffic versus some other parameter. And we need to be able to distinguish between the multiple attack types. All right. So supervised is a little bit easier, but unsupervised is probably for things like network attacks, where you would probably find the most benefit. Okay. So let's talk a little bit about AI for malware detection, right? Traditionally, antiviruses relied on signatures, right? Malware is polymorphic now, right? So it evades signatures. And the question always is, how do you catch something that's consistently changing what it looks like? So let's dive into this and see how AI can help us here, right? We can talk about it can do static analysis, right? So it looks at headers, import tables, section entropy, embedded strings, right? These are all features of the file that you don't need to execute the file for it to be parsed and acted on. And the AI advantage is that machine learning can identify malicious patterns, right? Because it's going to say, well, this is what normal looks like, and these are abnormal. And the complexity of it is that a human could never do that, right? Because you would have to go through and you would have to go through and scale and categorize and label and do all that other stuff. And it just, one person can only do so much. And you would never notice a lot of the patterns, right? Because a lot of times as humans, we do analysis, we look at one feature, right? We don't look at multiple features just because of the complexity. So this would be something like if your calculator app suddenly started opening network sockets, or it started modifying your registry, right? That's something you would probably want to do. So dynamic analysis, right, is you execute in a sandbox. So you fire it up on a virtual machine and you see what it does, right? And you look at it and you say, does it try and inject code in other processes? Does it establish a network connection? What is it doing? And because you have AI, you know what normal execution looks like. And you'll be able to spot this pattern and flag it as an anomaly. So, and you can have pattern recognition across thousands of behavioral features as opposed to just looking at, file by file by file. Let's talk about clustering, right? Clustering for malware families. Typically, when malware, even if it changes its signature, it retains a similar behavioral pattern. Remember the clusters that we looked at for DDoS, right? Your method might change, but the pattern is going to be the same, and that's similar with malware, right? So if you can group similar malware, you can predict the behavior of new variants. If it falls within reasonable distance, remember distance-based algorithms of this cluster, we would associate it with that and call it malware or not malware. So, and then we got zero-day detection, which is kind of the holy grail. It's like we're going to detect malware we've never seen before. And the AI approach would be something like SVM, where one class SVM, where it says, I know this is good, and anything that's not in the realm of good is bad, would be a mechanism you could use to find this. So, again, even if you have dynamic analysis, it might miss some malware because you have evasion techniques that malware authors use. But eventually, if you're looking at it and run it through your algorithm, you should be able to find out. Okay. All right. So again, this is another example that I created. And we're going to talk a little bit about malware versus benign software and talk about static analysis. Remember, static analysis, we are not executing the malware. We're just looking at the characteristics of the file. So this is somewhat similar. Remember when we looked at network traffic, the big mountain is good and the stuff that's not in the big mountain is not good. So we're simulating static malware analysis by generating synthetic features based on a real PE file, right? PE file format is typically used for executables. If you saw the description I gave of the VirusTotal data for the Capstone project earlier, that's based on PE file. So some of these names might sound familiar. The key concept is, right, we're analyzing without executing. We're just looking at the contents of the file. PE is a Windows executable format. So this is kind of Windows specific, but that's the way the world is. So we love Windows. Entropy, right? We measure randomness that can indicate packing or encryption, right? More randomness, less randomness. If you have less randomness, it might be packed or encrypted. API calls. Suspicious API calls indicate malicious behavior. You know, digital signatures, legitimate software is usually signed with a signature. If it's not, then it's questionable. And then you know, have that binary classification as a malware. So what are the key points here, right? Uh, you don't have to remember this. This is just specific for this example. But what this shows you is if you look here, you know, first thing we're looking at is file size, right? Look at the file size. What would you say just by looking at that? File size of malware is smaller than the file size of benign software. So that's one characteristic, right? So our algorithm knows that. The next thing is entropy, right? We just talked about entropy, right? Malware, just looking at the visual, has higher entropy than benign samples, right? So there's another feature that ML has found for us. Number of sections, right? You can see that typically benign software has a higher number of sections than malware, right? So there's a third characteristic, right? Same thing with number of imports. So now guess what happens, right? All these characteristics that are being teased out by your machine learning algorithm, if you meld these all together with a method, it would tell you what is malware and what's not malware, right? Because all these things add up. Is if you have all these characteristics and they all add up together, you're going to trip the flag. You're going to say it's malware, and that's how, you know, AI works. Is it takes the results, all these algorithms, and it determines whether it's good or not, and it should flag it, and it moves it forward, right? So we're not just relying on one characteristic to determine if it's malware or benign, right? So super important concept. I know this is like a lot to take in, but just think about it, right? Is if I'm a human, I might be able to figure out one of these things or two of these things, and I have to look at it across, you know, millions of files and that kind of stuff. And I'm probably not looking at all these other things in a way that makes sense. But if I'm able to use machine learning and artificial intelligence, it combines all these things together. And that's why the accuracy is a lot greater. Okay. Because you can see that there's some overlap between benign and malware among all these things. And figuring out where that decision boundary is based on all these different features that are important is where machine learning excels. So remember, each one of these things is a feature: file size, entropy, number of sections, binary features, suspicious APIs, number of imports. Every one is a feature. So each one of these is a column. And if you went through that column and you analyze what this was doing, what the mean is, you would have this one bit of information. But machine learning combines all this stuff together, tells you what the most important features are, and it helps you build an algorithm that finds this stuff. So that's pretty cool. Okay, sorry. All right. So what's the key thing? I just alluded to this about AI for malware detection, right? Feature importance, right? So what features do I care about? Um, you know, we talked a little bit about a PE file, right? The structure, suspicious indicators, right? Timestamps, section counts. AI can learn all these different patterns across millions of headers and help you determine what is potentially malware and what's not. So, so these are all different parts of this. I'm not going to spend a lot of time on this since this isn't like a deep dive into malware. But if you look at the characteristics of all these different things, so each one of these things again is a feature. Each feature, you process it, you scale it, it has a mean, it has standard deviation, And you're able to evaluate each one of these things by those characteristics, and evaluating all that information together is how a machine learning algorithm works and how you get AI to do stuff for you, right? So think about that. Each one of these would be a column. Each column has an average, which is a mean. Each one has standard deviation, which is where how far things are away from the mean. And anything that falls outside of it is an anomaly and gets flagged. And you're just able to do this on millions of rows and hundreds or thousands of features all at once. And that's the beauty of doing this machine learning, right? Because we could do this as humans, but we don't scale. All right. All right. So let's talk real quick about what an end-to-end process would look like. So there's a couple of things I want to talk about here. One is ROC evaluation, and that's this yellow line, and AUC, which is the area under the curve, right? So anything underneath this line is called out by the machine learning algorithm. So let's talk about it like this, right? So malware detection is a binary problem, right? It's a binary classification. Either is malware or it's not malware. It uses the ROC, the receiver operating characteristic curve for evaluation. You got to understand, right, what features are most important. The features typically that are most important are the ones that have the most deviation from the mean. Again, the distance, right? How far away is it from the mean? So if I'm a large number of standard deviations away from the mean, then it's anomalous and I probably want to look at it. So probability, right? What's the odds that I'm right or wrong? That's where the confusion matrix comes in. And then you need to have a classification report, which gives you the precision and recall metrics. So why do we care about ROC and AUC? This is something that you're going to get asked, right? And you need to understand this. Ask your LLM for a detailed description of ROC and AUC and read that, because it's going to stick with you a lot better than listening to me kind of blather around about this. But this is an objective way to compare AI systems. It helps you do threshold selection, right? It's a data-driven approach. It lets you do performance monitoring so you can track system effectiveness over time. And it's something, if you were evaluating a vendor that has a super whiz-bang AI box, ask them, what's the ROC and AOC for your product, right? And compare it amongst other products, right? And these evaluate the binary classification model, right? Which is really critical in cybersecurity. We have a lot of stuff that, is it bad or is it good? And you need to balance catching threats with false alarms, right? ROC is how well can this model distinguish between classes, right? For this particular example, the ROC curve is 1. It's perfect. Why is it perfect? You look at the confusion matrix and there's no issues, right? There's no issues with precision and recall. They're perfect. So we have got the perfect algorithm here, or we think we do, right? But this is critical because you can look at this and you can say, oh yeah, that's pretty good. I believe that, right? AUC, area under the curve, is how well do you distinguish between random and something that has a pattern, right? 0.5 is random, which is kind of anything below this dashed line to the right is 0.5 or less, and anything to the left is establishing perfection. So that's why this is somewhat important, right? And if you look at an ROC curve and you see that it dips below kind of that the AUC line, that's where you got to really start questioning. Okay, so and then the threshold selection, it's a business decision based on cost benefit, right? How good do you have to be with respect to the AUC, right? how much do you have to tread that line between random and not random? Okay, so this is simple, but it sounds really complicated. It's a graph that shows, so ROC is a graph that shows a relationship between the y-axis, which is true positive rate, and that's sensitivity and recall, right? Which is down here, right? These are the true positive rates, 100%. And the x-axis is the false positive rate, and this is specificity, right? So here in the light blue squares where you got zeros, right? We don't have any false positives. So that's why the ROC curve looks like it does, and we have the perfect algorithm. Okay. And then, the area under the curve, again, that's everything to the right of the ROC curve. And you can see that we have a perfect curve here, that the area under the curve is 1, which means it's the perfect classifier. And, you could obviously, point anything less than 0.7 is probably not great. And anything less than 0.5, which is this line, is useless, right? All right. So this is the probability the model will rank a random positive higher than a random negative. So is it random or isn't it random? If it's to the left, it's good. And if it's to the right of the blue line, it's bad. And these are good for binary classification and model quality, and when you have a balanced data set or when both classes matter equally. All right. Okay. So let's talk about this in action. Let's talk about Darktrace. It's a pretty hot company, right? Claims to be the most successful commercial implementation of AI for cybersecurity. And they've been doing it for about 12 years. And their claim to fame is that they use unsupervised machine learning for cybersecurity, right? So they try and map what's normal, and anything that's not normal gets flagged as an anomaly, which is different than traditional approaches, whereas we're going to try and guess everything and say these are the anomalies. And, you have to weed through and figure out if we're right, if we guessed right or not. So, it doesn't rely on signatures or rules or historical data from past breaches. And it uses unsupervised learning to say, is this normal or is this not normal, right? As opposed to traditional where is it a known threat or not? So what does this mean, right? I've said this before, your data, your activity in an organization has a shape. It has a pattern. I wouldn't go so far as to say it has a soul, but it has a unique signature of how things transpire. If you look at a network in a hospital and a bank, they would look completely different, right? So what good signatures do you in that respect, right? Every user has a distinct fingerprint. We talked about earlier, does somebody who normally logs in from Seattle suddenly log in at 2 o'clock in the morning from Estonia, right? That's kind of weird. And same thing with devices. They typically communicate in the similar patterns, especially if you're looking at Internet of Things, right? OTA. That all has a pattern. And what machine learning does, what unsupervised learning does, is it figures out what that pattern is. And in things that it doesn't fit into the patterns, it flags, right? And it clusters and says, hey, you should go take a look at this. So it does baseline learning by continuously monitoring. It does modeling by creating models of normal behavior using algorithms, simple as ones that we've talked about in our lab. and it dynamically updates the understanding of normal, i.e., it retrains its model in real time as the organizations evolve, right? So it's continuously updating its. So, in a hospital, you would expect medical devices to be communicating at 3 o'clock in the morning, but a bank, you wouldn't expect, an ATM in a lobby to be generating any network activity at 3. And it does mathematical models based on the probability of normal behavior versus non-normal. And again, as things evolve, it updates. All right. So again, Darktrace, their differentiator is that they use unsupervised learning, right? So most AI is based on historical data. What Darktrace does is they learn what's normal and they flag everything that's not. Remember, we talked about SVM as one class SVM is a good mechanism to do this. Bet you there's some one class SVM and Darktrace. We don't need labeled training data, right? We figure out what's normal and not normal, and we look at the clusters. And then this helps fold into your unique pattern of activity and the operational cadence of your network, right? It has a self-learning architecture that it continuously adapts, and it doesn't need signature updates. Hooray, signatures are terrible. And because it figures out what threats are and what aren't. So it has enterprise immune system, right? Sensors, data processing, AI models, and alert generation. Uh, it has unsupervised learning based on similar principles to our lab exercises, right? There's probably somebody using scikit-learn inside of there to do experiments. I can almost guarantee it. And they can do multi-dimensional analysis, like network communications, like the IDS example that we showed. User behavior, the behavioral clustering that we showed with the DDoS attacks, device patterns that extends anomaly detection, like we've been talking about, and data flows, right, related to malware detection and the network detection features that we showed, right? These are all techniques that are probably being used by Darktrace, right? So what are the results, right? Speed improvements. They claim they catch threats 99% faster with advanced AI. I could believe it if they had a fully trained model, right? So you have an advantage over traditional detection. MTTD, mean time to detect, I think is like 25 days, if I remember right. I mean, it's long, right? So that's traditional detection. Um, Darktrace says they do it in minutes or hours, right? This is useful because of lateral movement. If you've ever worked an APT incident, you know that looking for pivoting behavior and log analysis is lots of fun, right? We can have AI do that for us now, because if there's a user that doesn't usually do a bunch of logins to a bunch of random machines, and all of a sudden you see that activity happen, it's going to get flagged in an AI-driven system, right? Whereas you might just be looking at a graph model of the postmortem if you don't have an AI-enabled system, right? Um, so um, the difference would be, right, as opposed to having a signature, right, it takes a while to craft it and update it and then make the detection possible. The behavioral approach means that you see anomalous behavior and you generate the alert, right? So it's a much shorter time frame. You know, identity attack performance. This has been a big problem every place that I've ever been, right? It's been mitigated to some extent by the advent of things like, YubiKeys and things like that, where you shorten a token time to 19 hours. So you have to re-authenticate with two-factor. And but regardless, right, you still, I think statistically they say it's almost 300 days, right, for identity attacks, right? So it can be quite a bit of time. Darktrace says 24 hours. Who knows, right? That's marketing propaganda. So, but you could see with a behavioral approach as opposed to a signature-based approach where it would be able to tease this out, right? Because we have a baseline, we know how a user behaves, we detect the deviation, right? Unusual patterns. Think about what I talked about earlier with like Actimize and things like that. And you have an automated response, right? This is important. This is where AI is really changing the game, right? Where it takes action automatically. It could do everything from the standpoint of let's just start a forensic data collection, right? So I've got a sense of logs and they're front and center for my analysts. To actually, I can shut a port. I've implemented systems like this where if we detect bad activity, we put you in quarantine in a VLAN that doesn't have access to the corporate network or to the internet, and then we come and see what the heck it is that you're doing. All right, so Darktrace says that they detect like things like ransomware attacks, and they stop them before encryption can begin. This is important. Things like healthcare. It seems like they get nailed a lot by this. Um, you can have millions in downtime and regulatory penalties. I've experienced this somewhat firsthand. Had a relative in a hospital when they had a ransomware attack and they had no computers. They were running things around on paper and stuff like that. That took them days to get their stuff back together. So, having this kind of technology that claims it can do it in hours and minutes at the speed of light is super important, right? Um, so, what they said happened was that there, and stop me if you've heard this before, phishing email, right, gets by, uh, credentials get snarfed, attacker uh, moves laterally, uh, it goes through, it elevates privilege, uh, and then they start encrypting files with something that is behavioral, like Darktrace. They claim anyways that they're going to detect the anomalous activity and quarantine it or flag it before it gets to the point where they're doing encryption, and that their system can automatically contain the threat. So that's really the future, right? Is you have AI aware systems that detect anomalous behavior and take action without intervention. Um, I prefer having a human in the loop at some point, right? Right. Maybe you can do the additional containment, but a human analyst has to go look at it after it's been contained within a certain number of time, right? Otherwise, you could potentially cause an outage. So, um, you know, uh, I'm not 100% down with fully autonomous, but I think you need to have a human in, right? But you could avoid millions in downtime and have better patient safety and things like that, and your reputation stays clean if you have something that is based on anomalies as opposed to signatures, and you're going to get better results. So that's Darktrace's claim to fame, right? Uh, so what does this demonstrate? There's several things that we've talked about. Anomaly detection, right? We looked at an isolation forest example earlier. Uh, Behavioral analysis, like the clustering that we showed for the network attacks. Pattern recognition, identifying attack progression patterns, right? Pivoting and those types of things, right? That's all anomalous activity. And then it has automated response, right? AI drives the containment decisions, and it helps put you basically in timeout so you can't do anything bad. All right. So benefits, right? Scalability, right? AI can scale and process you know, probably terabytes of data daily, right? There's no human team that can handle that volume, right? Think of you going through and trying to triage alerts and things like that at that volume. It would be insanity, right? You have faster response times for threat classification and real-time learning, right? So you learn what's a threat faster, right? If you're doing an anomaly detection, all of a sudden you have a cluster, you can pick that out. We did this a long time ago at Microsoft back in like 2005, 2006. We used to look at Windows event reporting data for evidence that people were being dumb and testing malware and exploits on servers. And when they crashed, they were still letting them send us error reports. So that was super cool. But the downside of that, right, is that we saw that and then we had to generate signatures and things like that, push them out. Whereas if you had a real-time system, it would automatically do that for you. It would flag it as an anomaly. Reduce false positives. You're taking a deeper look at things instead of a signature based, which is generally so loose. You generate a lot of false positives. And you can find a 0-day through behavioral analysis. It may not match an existing pattern, but if it's clustered with something that's identified as anomalous, it can be identified, right? Catch things during reconnaissance, right? You can see anomalies before there's actually an attack. If you've ever done investigations looking at a timeline, you can see where things happen and take action based on that, right? So it's really the big benefit of doing something like Darktrace is the fact that it's behavioral based. Okay. So then last but not least, I'm just going to skim over this, but this is again from our example data. And this is showing, like behavioral analysis based on the data that we had and the types of things that had the most variance, right? The features and stuff like that. Features and clustering. Again, I'm just going to gloss over this. We've been at this for quite a while, and I want to leave a little time for questions. But this is the example of like the file access data download, and you can see, right, anomalous activity or at least clusters that you could investigate to see what was going on. All right. So what did we talk about? Anomaly detection, right? Isolation forest. We talked about AI enhanced IDS, multi-class classification and behavioral analysis, malware detection, static analysis, random forest classification, feature engineering for malware identification, right? Is it malware? Is it not malware? Is a dirt simple? Okay. Clustering based on behavior. We just looked at that. User behavior analysis over time. DB-scan clustering for insider threat detection, outlier identification, user patterns. Real-world applications like SOC, endpoint detection, network traffic analysis. Everything is using this for AI, right? For threat detection. This was all done with Scikit, right? This was all done with Scikit, and I asked Claude to write me this code, and I hacked on it a little bit, and I got all this stuff to work, right? So you can do this too. And then the big things we want to talk about is, accuracy. How correct is it? What's the precision? True positive, recall, catch as many real threats. F1 scores the balance between precision and recall. And ROC and AUC is the model's ability to distinguish between classes. All right. So key takeaways, right? AI is an enhancement, right? For handling things. It's faster. It can handle more data. Anomaly detection versus signature based, right? It figures out how things cluster together and how it differs from normal. AI improves IDS as opposed to signature based. It becomes behavioral. ML is crucial for identifying polymorphic and 0-day malware, right? Because you can change the signature, but the behavior is similar, and it gets clustered in with other things that are known as malware, and it gets identified. And real world systems integrate AI all across the detection pipeline. A couple other things I wanted to show you. These are artifacts that I had, and these need some work, but I just wanted to show you some of the stuff that you're able to generate using ML. I asked Claude to generate these for me. So this gives me an attack timeline, right? This is pretty cool because I can go in and I can hover over, let me see if I can make this bigger. Right, I can hover over a spot on the timeline and it tells me what the type of the anomaly is and when it happened, right? It can tell me the ports and destinations and things like that. So this is just a quick example, right? I said, hey, can you show me, can you generate a attack timeline for my IDS? And this is what it gave me. Now here's another thing too, that this is pretty cool. I asked it for a dashboard and this is what it came back with. Again, this needs some work, but this is the kind of stuff, right? How many of you would get super kudos brownie points for doing uh, an attack dashboard for your network traffic, right? Here it is, right? That you can get this kind of stuff done. And again, I'm not a Java developer. I'm not HTML developer. I'm not a Python developer, but I can do this stuff because I have the ability to hack stuff that AI gives me and get results. So this is all based on that same synthetic data set that we just looked at. And it takes what we have here in this notebook and it puts it in a dashboard, right? So this is how you get from your proof of concept to what we're looking at here. All right. So that was a lot. Got a few minutes left for questions. If anybody's got any brains left that haven't melted out of your head.
Hey, Stephen. I have not a question, but I just wanted to show you something that I produced real quick.
Mm-hmm.
Do you mind if I share?
Yeah, go ahead.
Thanks, man. Not the current only. Oh, here we go. Got it. Bang. So check this out. One of the things that I did with my solutioning for homework 2
Yep.
is I did take the data and create a correlation heat map.
Cool. I like
For
action heat
data.
maps.
So I kind of worked that in. The other thing that I did that was pretty cool is basically like I took our original like the homework, right? And I
Yep.
just went, like element by element and created that Python code. And then
Hmm.
I like compiled it so I could put it all together
Yep.
into one cell and get it to run properly. And
Yep.
then once I did that, I went back to my LLM and I put my code through that and asked it for a vulnerability report.
Yep.
So I was able to create an artifact of vulnerability for my code and then also implement corrections and then document those corrections.
That's great. That's a super good example of how you can iteratively leverage your LLM to give those results. If you're sharing, I don't see anything.
Oh shoot, I'm so sorry. I'm so sorry. Shoot. Gosh darn it. I am not sharing.
Oh
Oh,
wait.
here we go. Here we go. Sorry, sorry, sorry. I just needed to update my settings.
Okay.
Security, right?
Yeah.
I'll be
Uh-oh. Okay. Anyways, I'll share again while we're waiting for him. Okay. All right. So next steps, right? You got to experiment. The only way that you're gonna figure this stuff out is to play with it. If it doesn't work, ask your LLM for help. Ask it to explain the code. This is super important, right? It can explain it'll write a ton of code for you, and then it'll explain it and tell you what it's doing, and that's really helpful, right? Try your own data sets in feature engineering, right? Go get a log file or an example from the like OSTF that I shared, securitylogs.com, I think is it, or securitydata.com. But get a log and ask LM, say, hey, here's the log sample from this website. Can you create a function that does something for me? right? Okay, Andrew had to restart. Okay, so uh, the way to get good at this is to play with it. Look at deep learning, right? Neural networks, um, adversarial AI defensive techniques. Ask your LLM, describe adversarial AI and defensive techniques, and see what it comes back with. Play with and build your own threat detection system. Kind of like what Andrew's talking about. Find the things in these different cells and put them together. You've seen these apps that are, I mean, obviously they need work, they're not production ready, but before AI, I could never have written like 2,500 lines of Python code. I don't think I've written 2,500 lines of Python code in my whole career before. But it's a powerful force multiplier that you can use to ask questions to and get results, right? But you gotta be curious about it and you gotta play with it and ask the LLM when it breaks something, ask it to fix it or ask it to explain it and ask it where the problem is. All right. Okay, so next class, we're going to talk about supervised learning for intrusion detection. Remember, supervised, we know what the answer is, and we're just training to find things that look like the answer. As far as further exploration goes, look at different AI-driven security products, see what's out there besides Darktrace. Look at open source threat intelligence platforms, use AI, see what's out there. There's all kinds of stuff, MITRE ATT&CK, what have you. And, start broadening your horizons. Again, use the LLM to help you to answer questions and provide results, right? It's the only way to go these days. It's like super Google. You don't have to go and troll through Stack Overflow anymore. And be curious. Do your own projects. See if you can get your own results. Look at them with a critical eye. See if they make sense. I don't know how many iterations I went through for the example for this lecture, but I had to go through some back and forth with the LLM and some hacking on my own to get it to work. But in the end, it's a pretty good example, right? I mean, if you could turn out something like that, that's a year's worth of work for a lot of people. So you definitely can do this, and you just gotta like jump into it. All right,
Hey,
that's all I got. Yeah.
real, did you see that that markdown file I put in chat?
No, I didn't.
I broke OpenAI last night with an open logic loop.
Oh, nice.
And then I captured it.
That's good. Yeah, that's next. We're all going to be AI hackers.
Right?
Yep. Very cool. All right. That's all I got, unless there's something else in 2 minutes. And Andrew, I'd like to see what you've done. So maybe Tuesday, we'll take a few minutes and you can show that off.
Yeah, 100%. Yeah. 100, like happy to.
All right, anybody else that's got something cool, post it in chat, throw it up in GitHub. Jose, you got a question?
Yeah, I was kind of struggling a bit th- to on how to decide when to one hot encode versus label encode. And I was like, I asked Claude for like a couple times. Like first time it looked at like cardinality and to give me some like functions on how to determine it. And then I went back and kind of asked ChatGPT the same question and it gave me like different answer. It only went through and ChatGPT was only suggesting to uh, one hot encode two of the fields. And so when I told Claude about it, it was like, oh yes, you're right. And so it arrived at one hot encoding only two of the fields. So could you at least help explain a little bit more like or recap on like when
Hey,
to use
hey,
each?
I have a little guide I'll post in chat that talks about when to use label encoding in one hot. I'll dig that out and post it. So uh, so everybody has it. Okay.
Okay, great. Thank you.
Is that cool?
Yeah.
All right, right on. Okay.
I also have a markdown file for my interaction with my AI for deciding between single or one hot. So I'll just post that in the Discord.
Okay, cool. All right, I appreciate that, Andrew. All right, cool. All right. I know that was a lot. Hopefully it didn't blow anybody's mind too much, but remember the principles, right? Is we're looking across a number of different features and looking at the variance in those features, and that's how we build ML models, is by the combinations of the multiple features. And that's the benefit of doing it as opposed to just a human looking at it. So you still need a human to look at it to make sure it makes sense, that it's explainable, but the ML algorithms do the heavy lifting. All right. Okay, folks. Have a great weekend. As always, I'll be lurking on Discord, email if you got questions, and we'll get the recording and the slides and stuff posted for everybody. And the chat, homework is due, right? But I get it. Just as long as you get it in before the end of the class, we'll get it graded and you'll get credit for it. So that's all I got. Anybody else got anything? All right.
No,
That's all I
thank you.
got.
Hey,
Going once.
quick question.
Yeah, you bet.
So I uploaded the original coursework or pardon me, my original response for the initial install and setup and all that stuff.
Yep.
I have some other artifacts that I can add. Can I just add those along with my homework too?
Yeah, or I could send homework one back and you could resubmit it if you wanted.
Yeah, whatever's easiest for you.
Yeah, I don't know how you can add on. That sounds like a Paulina question. But
Paulina,
if
I'll coordinate with her on Discord.
all right, but if you need to, I can send back your original submission and you can submit it again. That would probably be the easiest thing.
Whatever's easiest for you.
All right,
Thank
man.
I can also do that, so feel free to reach out, Andrew.
Awesome. I will reach out to you on Discord then. Thank you.
All right. Have a great one. See you later. Bye.